Okay, let's get started. Welcome back. This is the 12th lecture of the condensed matter course. Hello? Hello? Is it Monday still? So when we left off, we were talking about scattering. The standard scattering experiment is you have some sample. You send in some wave at wave vector k, and something comes out at wave vector k prime. And by measuring what comes out at various wave vectors k prime, we're supposed to be able to deduce the structure, the microscopic structure of the sample. And I want to emphasize again that this type of experiment is the way to understand the microscopic structures of things on scales smaller than you can actually see with your eye. The number of Nobel Prizes that have been awarded for people doing this type of experiment is enormous. There's like 20, 25, 30 Nobel Prizes. Just a couple of famous ones, Oxford's own Dorothy Hodgkin, Somerville's favorite daughter, won a Nobel Prize for discovering the structure of penicillin and insulin using X-ray scattering. Watson and Crick very famously figured out the DNA double helix structure, which they figured out by looking at X-ray scattering data taken by Rosalind Franklin. Rosalind Franklin sadly died extremely young and was therefore denied a Nobel Prize as well as the rest of her life. Which is very sad, but everyone should know her name nonetheless. Anyway, this is an extremely important experiment, and that's why we're spending so much time on it, at least this lecture, next lecture, and maybe some of the lecture thereafter. One of the things we derived in the last lecture is that in order to get scattering from k to k prime, we must satisfy in a crystal the Laue condition that k minus k prime must be a reciprocal lattice vector G. Now, at the very end of the last lecture, I claimed that this condition, this Laue condition, is very similar to a condition that you have already thought about when you considered just simple diffraction off of planes. If you have light or X-rays or something, or neutrons coming into a set of parallel planes, a family of lattice planes, and you have we understand how you can get diffraction of this sort at certain angles off of a parallel family of planes. And I'm going to claim that this condition here is actually equivalent to that. So first what we're going to do is we're going to review some things about diffraction off of planes. Then we're going to show that the Laue condition and the diffraction condition are the same. So let's abstract this picture a little bit to just a set of planes like this. And we'll imagine we have some wave coming in like this. It reflects off like this at an angle theta, but also another parallel wave coming in like this, exactly the same wave, just goes down to one layer further, diffract off like this, the same angle theta, like this. And I'm going to actually emphasize this, and maybe I'll even write it down because it's an extremely common source of error. Total deflection angle equals 2 theta. Why is that? Well, there's theta there and another theta there. So the difference in angle between the incoming wave and the outcoming wave is actually 2 theta. This causes all sorts of grief to a lot of people, so make sure you know when you're talking about theta and when you're talking about 2 theta. So as you did this type of calculation in prior years, you know that what you need to do is you need to calculate the additional distance traveled by the second wave. So if I drop a perpendicular here and a perpendicular here, the additional distance here is d sine theta, if d is the distance between the layers. So in order to get constructive interference, maybe I'll write this first. The additional distance is then 2d sine theta equals 2d sine theta. So it's d sine theta on this side and then another d sine theta on that side. So the additional distance taken by the wave that reflected off the second plane is 2d sine theta. To get constructive interference, I think as the term goes on, my writing gets worse. So we get is n lambda equals 2 sine theta. So you have to have an integer number of wavelengths contained in that extra distance. Does that all look familiar from previous years? Yeah, okay. So I'll put a box around it because it's an important equation. This is known as the Bragg condition. Bragg condition. After William Henry and William Lawrence Bragg, the father and son team who pioneered X-ray scattering. William Lawrence Bragg winning a Nobel Prize at the age of 25 for his work on X-ray scattering. For a chocolate bar, does anyone know who the second youngest Nobel laureate was? It's a name you all know. Those are all really good guesses, but those are all wrong. Really close to all of them. Same era. Heisenberg, who said it? Up there. Oh my gosh, all right, close enough. Yes, Heisenberg. Second. Dirac was just a few months older than Heisenberg. All right, so now what I claimed to you was that this condition, this Bragg condition, is actually for getting constructive interference. You only get constructive interference coming off on certain angles from your crystal. That condition is actually the same condition as this Laue condition over here, which is the conservation of crystal momentum. So let's see if we can prove that. Let me write this down because this is an important proof. Equivalence of Bragg and Laue. Okay, so same diagram. We have two parallel planes in a family of lattice planes. You can kind of understand why it is that these two are going to be related. Remember from last lecture that reciprocal lattice vectors are associated with families of lattice planes. So that G up there is going to be telling you something about this family of lattice planes. So the fact that we have parallel planes is because we have a reciprocal lattice vector. Those are sort of equivalent statements. So here we have our family of lattice planes separated by some distance d. We have an incoming wave at wave vector k and outgoing at wave vector k prime. And then since we have a family of lattice planes, there is a orthogonal vector g, which is a reciprocal lattice vector. That was one of the things we derived last time, that every time we have a family of lattice planes, there's a reciprocal lattice vector perpendicular to it. Since we have elastic scattering, the magnitude of k and the magnitude of k prime are the same, and let's actually define some unit vectors, vex k hat, k prime hat, and g hat to be pointing in the appropriate directions. And then with a little bit of geometry, k hat dot g hat equals sine theta. Just take a second, make sure you're convinced of that. If k hat and g hat were pointing in the same direction, then k hat dot g hat would be 1. Sine theta would also be 1 in that case. Whereas k prime hat, which is going in the opposite direction, dot g hat is minus sine theta. Okay? And we can also use, we're going to need that k vector we can write as the magnitude of k, which is 2 pi over lambda, with lambda the wavelength, times k hat. Everyone happy with this so far? Yeah, okay. Good. So we're going to assume the Laue condition. So assume Laue. That is k minus k prime equals g. So assume that's satisfied. And I can rewrite that then as 2 pi over lambda times k hat minus k prime hat equals g. Then dot with g hat to get 2 pi over lambda g hat dot k hat minus g hat dot k prime hat equals g hat dot g vector. Okay, then we'll substitute in. We just had that g hat dot k hat is sine theta, so we'll substitute that in. So we get 2 pi over lambda. So this is sine theta here. The second term is minus sine theta. And then g hat dot g vector is just the absolute value of g vector. Everyone still happy? Okay. No? Not happy? Yeah? Still happy? Okay, so just a little bit of rearrangement. This becomes 2 pi over absolute g vector times 2 sine theta equals lambda. And now remember what we said, what we derived last time about reciprocal lattice vectors. The spacing between lattice planes, d, is 2 pi over the shortest reciprocal lattice vector in a given direction, g min. So any reciprocal lattice vector, g vector, has to be some integer times the minimum lattice vector in that given direction. So n is some integer. So substituting this equation and this equation into the equation just above gives us 2d sine theta equals n lambda, the Bragg condition. So what we've shown is that the Laue condition, this conservation of crystal momentum, is the same thing as requiring constructive interference or having the Bragg condition satisfied. Okay? Good? All right. So supposing that we have the Bragg condition or the Laue condition satisfied, one of the things we derived last time was that the intensity of scattering is proportional to the structure factor at g, k minus k prime, squared. When the structure factor, S, equals the Fourier transform of the scattering potential, V of r. Does that sound familiar from last lecture? I hope. Okay. But that still leaves open the question, what is V of r? And what V of r is, what the potential your wave feels as it goes into the crystal depends on, well, it depends on the crystal, but it also depends on what kind of wave you're using. You know, the wave interacts with the crystal very differently depending on the type of wave that you're using. So the easier case to think about is neutrons. So case 1, neutrons. Neutrons interact mainly via nuclear forces, via short-range nuclear forces. Nuclear forces. So what does that mean? It means the neutrons go into the sample and they see very short-range potentials associated with the nuclei, and we can write that V of r equals, or it's proportional to, I guess, sum over atoms, all atoms alpha in the whole system, some coefficient B alpha times a delta function potential at r minus r alpha. So basically saying that every nucleus, so r alpha is position of atom alpha, and B alpha is the magnitude of the interaction with that nucleus. It's known as the nuclear scattering length. And so the essence of this equation is basically saying that the neutrons coming in, they see very sharp peaks in potential at the positions of the nuclei. And that's all. They don't see anything else. Now, these coefficients B, they have to do with nuclear physics, and nuclear physics can be extremely complicated. They can be positive or they can be negative, depending on the particular nucleus we're talking about. Positive means you have a repulsive interaction with the nucleus. Negative means you have an attractive interaction with the nucleus. And you can have either. And the size of these B's can vary, by lots depending on the particular nucleus you're thinking about. And really the only way to know what B is for a particular nucleus is to just look it up on a table or measure it. You could have two atoms on the periodic table that are right next to each other, like carbon and nitrogen, and the nuclear scattering length is completely different. Some can be positive, some can be negative. It just goes all over the place. So it's actually something that we can't actually predict very easily. Even nuclear physicists, even good nuclear physicists, have a hard time predicting these things. So we just have to resort to a table and assume that these things are known, or that somehow we're going to be able to measure them. But given that we have this sort of functional form of the interaction with the nuclei, we can then calculate the structure factor S of g, which, remember, the definition is that it's actually d3r, it's the Fourier transform in the unit cell, of e to the I g dot r times v of r, something we derived last time. And if we actually plug in the form that we just wrote down above, we have sum over alpha, b alpha, delta, three-dimensional delta function, r minus r sub alpha. Now we'll let the delta function act, and we get the fairly simple outcome that the sum over atoms alpha in unit cell of b sub alpha e to the I g dot r sub alpha, where r sub alpha is the position of atom alpha in unit cell of atom alpha. So there we have it. So that's the structure factor for scattering of neutrons against nuclei. Now, that's for neutrons, neutrons being fairly simple, but there's a second case that we need to worry about, which is X-rays. And X-rays are more complicated. X-rays, well, they're electromagnetism. X-rays are, like light. They mainly scatter from electrons. From electrons via Thomson scattering. You studied Thomson scattering last year? Does that sound familiar? Yeah. So they're mainly scattering from electrons via Thomson scattering. There's a little bit of Thomson scattering off the nuclei, but really very, very, very small amount because the nuclei are very heavy compared to the electrons, and so they're very hard to scatter off of. It's hard to push them around. It's easy to push the electrons around because they're light. So mainly, V of r for X-rays, the effective interaction, is proportional to the density of electrons. Density of electrons. So what's the density of electrons? Well, we can write sort of an approximate expression for the density of electrons, which we'll write as sum over atoms alpha. Z sub alpha, Z here being the atomic number of atom alpha. Atomic number being the number of electrons in the atom, also the number of protons in the atom, times some function, which I'll call G sub alpha of r minus r alpha, which I guess we can call something like a shape function, which is normalized, so its integral is 1. And we can compare that to what we have over here. It looks kind of similar, except here it's a delta function, and here it's not a delta function. So the difference being that if you're a neutron, you scatter off of only the nucleus, whereas if you're an X-ray, you scatter off of the whole atom. So you can kind of think of this G as being a very, very fat delta function. It's spreading out the delta function into some function that takes into account the entire size of all the electrons in the atom. So think of it as a sort of a fat delta function. So now I should say, however, that this form where we're summing up over the shapes of all these different atoms times the number of electrons in each atom is a little bit approximate. And the reason it's a little bit approximate is because there's an assumption, a hidden assumption here, that the shape of the atom is independent of its environment. If an atom happens to be bonded to one particular type of atom, it will actually distort the electron cloud of the atom a little bit. So the shape will change a little bit, and we've ignored that. And if it's bonded to a different type of atom, its shape will change a little bit in maybe another direction. It will depend on which direction it's bonded and so forth and so on. But to a very good first approximation, this is a fairly good way to describe the shape of the density of electrons in any crystal. Just, you have a shape for a particular type of atom, and you add it up over all atoms, and you ignore the fact that neighboring atoms will distort the shape. Okay? Good? Good. All right. So we can take this form of the density of electrons and, again, construct the structure factor, S of G, which is now sum over all atoms alpha, integral d3r, very similar to what we did just over here, over the unit cell. Then we have e to the I g dot r. We have z sub alpha, and we have g sub alpha of r minus r alpha. If we do that Fourier transform, what we get is extremely similar to what we get over here. Very similar to this equation here. What we get is of the following form: sum over atoms alpha in unit cell of e to the I g dot r f sub alpha, use a different letter, as a function of g. This is known as the atomic form factor. Form factor. It depends on the type of atom we're talking about. And if you want to know what the atomic form factor actually is, so actually, maybe just compare it to over here. The atomic form factor takes the place of the nuclear scattering length over here. Of this takes the place of the B alpha. But the overall structure of that, of the structure factor here of this equation stays pretty much the same. The only difference is the atomic form factor is also a function of the reciprocal lattice vector g, whereas over here it's not. And the reason it's not over here is because we have a nice simple delta function interaction over here, and we have a more complicated interaction over here. If you want to know the actual form of f of g, it's actually an integral d3r. It's just the Fourier transform g dot r g sub alpha. I guess maybe z sub alpha. Put the z sub alpha first, then g sub alpha of r. So it's just the Fourier transform of the shape function g. The surprise maybe is this integral is actually over all space, not just over the unit cell. And that, I'm not going to go through the whole derivation. I think there's a revision homework assignment that asks you to try to work through it, maybe, or there was last year. Maybe it's not there this year. But it's worth trying to do. It's in the book. But to try to convince you that the integral should be over all space, let me make the following argument. So these shape functions g have long tails. I mean, the tails are small, but they go out a long way. If you're only adding up over atoms within the unit cell, you would never feel the tail of one of those shape functions, because you're only adding up over alphas within the unit cell. But you should be including the tails of all your neighbors. So there's atoms way out there in other unit cells, then you should be feeling the tails of those shape functions. And so the fact that you're integrating over all space is keeping track of both the short range part of g and the tails of the g's from other atoms farther away. So they all sort of get resummed and come into the form factor here. Okay? So I'm not going to do the derivation. It's probably not worth doing, but might be worth doing for fun. Anyway, the form of this form factor more or less looks like this. So we'll draw f alpha here. We'll draw g over here. For g equal to 0, equals 0, f sub alpha is just z sub alpha. It's just basically counting. You can kind of see if you insert 0 into that integral all over space, g is a normalized shape function, so you just get z back out. So if g is 0, you get z sub alpha up here, but then it sort of decays slowly down to something much smaller, and the decay length is more or less 1 over the radius of the atom. Radius of atom. Very frequently, people just make the approximation that f of alpha is a constant, and the constant is just the number of electrons, because if you have more electrons, you scatter more off of the atom. So just let's assume that the form factor is independent of g and is basically just proportional to the number of electrons in g. It's not a horrible approximation. It isn't completely right, but it's not too bad, and it makes your life a lot simpler. It makes the X-ray problem look a lot more like the neutron problem, where this form factor, this b, doesn't depend on g anymore. It doesn't depend on the reciprocal lattice vector. But strictly speaking, f should decay as a function of g as well. So generally, whether we're talking about X-rays or we're talking about neutrons, we'll always have S of g of the following form: sum over atoms alpha in unit cell, e to the I g dot r alpha, and then, well, I'll write it as f of g, but or b sub alpha if we're talking about neutrons. It's convenient frequently to rewrite this in terms of Miller indices. So if we rewrite these statements in terms of Miller indices, we would have sum over alpha in unit cell, e to the 2 pi I, h times u alpha plus k times v alpha plus L times W alpha of F sub alpha HKL. So here, HKL is the Miller indices of G vector, and U alpha, V alpha, W alpha equals position of atom alpha in unit cell. Okay, that make people happy? Good so far? All right, let's actually do an example to make some of this more clear. So example, a material we talked about before, cesium chloride. So you remember cesium chloride is simple cubic with basis, and the basis has a cesium at 0, 0, 0, 0, 0, 0, and a chlorine at 1/2, 1/2, 1/2. And actually, I think I may have a picture of that. Yeah, I hope this looks familiar. We spent some time discussing it. So using that expression for the structure factor, we can write S at HKL equals, okay, so it's going to be a sum over the two atoms in the unit cell. So the first atom is at 0, 0, 0, so e to the 2 pi, then we have a bunch of zeros upstairs. So the first term will just be F cesium, because e to the 2 pi I 0 is just going to give you 1. Good. And the second term will be F chlorine times e to the 2 pi I, and then we have H times 1/2 plus K times 1/2 plus L times 1/2. Okay, plugging in the position of chlorine, U, V, and W both being 1/2 for chlorine. And I can rewrite that as FC, as strictly speaking, I should have given F cesium and F chlorine HK and L dependencies, as I just ranted about up there. So they're, strictly speaking, they're also functions of HK and L, weak functions of HK and L as well. They depend slightly on the magnitude of G. So, but I typically won't write that dependence, but you have to remember that it's actually there. So we can rewrite that as F cesium, and here I'm going to drop the dependence on HK and L for convenience, times F plus F chlorine, and this factor of e to the 2 pi I, H times 1/2 plus K times 1/2 plus L times 1/2 is actually minus 1 to the H plus K plus L. Good? So this is the structure factor, and you square this thing. This will give you and when you square it, it will give you the amplitude of scattering to with K minus K prime given by Miller indices H, K, and L. Okay? All right, let's do another example. Example 2, X2, pure cesium. Pure cesium. Now you remember that that's BCC, but BCC can be thought of as simple cubic with a basis, where the basis is cesium at 0, 0, 0, and cesium at 1/2, 1/2, 1/2. So in other words, we're just replacing the chlorine by another cesium. We discussed this before. And so there's the picture of it. So you just replace the chlorine with the cesium. So we get exactly the same result, except now F chlorine, this is the chlorine from the center of the conventional unit cell, it's going to be the same as F cesium. So now we'll get S HKL equals F cesium plus F cesium times minus 1 to the H plus K plus L. And if we want to, we can factor out the F cesium and write F cesium times 1 plus minus 1 the H plus K plus L. Now you'll notice that this vanishes unless, write this down, vanishes unless H plus K plus L is even. H plus K plus L is even. This is what's known as a selection rule or a systematic absence. Maybe I'll write those down. Selection rule or systematic absence. Systematic absence. Systematic absence. The idea being that you will get no scattering unless h plus k plus l is even. So all of the Miller indices with h plus k plus l being odd have no scattering at all. They are systematically absent from the scattering. Or in other words, in order to get scattering, you must satisfy this selection rule. And this is generally true for BCC lattices. These are the selection rules. Now, so whenever you do a scattering experiment, if you discover that all the Miller indices scattering by these wave vectors with h plus k plus l, if you discover that h plus k plus l odd, that there's no scattering at those Miller indices, but you do find scattering for h plus k plus l even, it's a very, very good bet that what you have is a BCC lattice. However, you can be fooled. How can you be fooled? You can be fooled, for example, let's consider the case of cesium chloride. Suppose, just coincidentally, F cesium and F chlorine were equal to each other by some coincidence, in which case you'd get the same vanishing over here. You'd have the same selection rule. But if they're different, maybe by a little bit, then the selection rule is almost satisfied, meaning that you'd have to look really, really carefully to see that there was some amplitude, because these would almost exactly cancel. So cesium chloride does not have this property. F cesium and F chlorine are not very similar. But there's a very, very similar material for which these two are extremely close, and you might be mistaken. If you looked at the data, you might make a mistake, and unless you looked at it really carefully, you would think that you would have the same selection rule. Anyone want to guess what that material is? What? Potassium chloride. You said that? Way up there? I'll give this to you anyway, but it's not the right answer. Potassium chloride is a very good guess, and the reason potassium chloride is a good guess is because remember that these form factors are basically proportional to the atomic number. And the atomic number of cesium and chlorine are extremely different. Chlorine is, what is chlorine? Chlorine is number 17, and cesium is number 55. So these two numbers will be extremely different. But if you replaced the cesium with potassium is right above it on the periodic table, it's chemically very similar, then potassium has atomic number 19 and chlorine has the atomic number 17. So these would be pretty close to each other, and you'd have a near cancellation. Potassium chloride is not the right answer because, in fact, potassium chloride does not take this crystal structure. And it takes a different crystal structure. It's FCC. It's like sodium chloride. It's FCC with a basis. There's another material, but that's a hint. What's the other material that would be more like cesium chloride? No, not magnesium. No. All right, I'm going to eat this one myself. It's cesium iodide. If you replace chlorine with iodine, which is two spaces under it on the periodic table, the iodine has atomic number 53 and cesium has atomic number 55. So the cancellation between these two would be almost exact. I mean, only within a few percent you would have slight non-cancellation. So it's very easy to make the mistake and look at the data and think that you have a BCC lattice because you think there's a systematic absence. But if you look at it much, much more closely, you discover that, in fact, it's not perfectly canceling. Okay? Everyone happy? All right. So, right. We can do the same thing with FCC lattices. Let's consider the case of FCC. FCC lattices. So for FCC, we can think of FCC equals a base, simple cubic times a basis, simple cubic times a basis. Incidentally, I should have mentioned this. If we were looking at nuclear scattering lengths, then there's absolutely no reason you should ever expect any two would be the same, independent of their atomic number. Because I mean, you could have a strange coincidence that the scattering length of hydrogen happens to match the scattering length of iron or something crazy like that. But just because they're close to each other in the periodic table doesn't mean that they have close nuclear scattering lengths, completely unrelated. So it's sometimes good if you think there's a near cancellation to switch from X-rays to neutrons, because a near cancellation with X-rays won't be a near cancellation with neutrons generally. All right, back to FCC. FCC, we can think of it as simple cubic with a basis, where the basis equals 0, 0, 0, 0, and 1 half, 1 half, 0, and 1 half, 0, 1 half, and 0, 1 half, 1 half. Actually, I think I have a picture of that as well. Remember this from a couple lectures ago. The FCC lattice is 4 interpenetrating simple cubics. Okay? So we can write the structure factor. The structure factor is going to be the sum over all these 4 lattice points within the conventional unit cell of e to the 2 pi I, and I'll abbreviate this, HKL dotted into UVW, point alpha, which we can then write as 1 plus e to the I pi h plus, so 1 is from 0, 0, 0, then we'll have h plus k plus e to the I pi h plus L plus e to the I pi k plus L, which is then equal to 1 plus minus 1 to the h plus k plus minus 1 to the h plus L plus minus 1 to the k plus L. And I claim that this vanishes unless HK and HKL all even or all odd. And to convince you of that, if HK and L are all even, then all those sets of exponents are even, so it's 1 plus 1 plus 1 plus 1. If HK and L are all odd, then again, 2 odds added together always give you an even, so it's again 1 plus 1 plus 1 plus 1. But if you have, for example, 1 odd and 2 evens, let's think about that case. Let's suppose H is odd and K and L are even. Then H plus K is odd, H plus L is odd, but K plus L is even, so we'll have 1 minus 1 minus 1 plus 1, and it vanishes. And you can convince yourself that unless H, K, and L are either all even or all odd, you'll get, it will vanish. So this is the selection rule for FCC. So where do these selection rules actually come from? If you remember back to the last lecture or the lecture before, we discussed families of lattice planes and how it is that certain sets of Miller indices do not correspond to families of lattice planes for BCC and FCC lattices. So remember, for example, with the 1, 0, 0 family of lattice planes, or reciprocal lattice vector, corresponds to these sets of planes for simple cubic. If I tried to use that 1, 0, 0 for BCC, it would not be a family of lattice planes because you would miss the guy in the center of the conventional unit cell. You have to go up to 2, 0, 0 in order to get that the extra plane in the middle, a smaller plane spacing, in order to catch that additional lattice point in the middle of the conventional unit cell. Okay? Does this sound familiar? Vaguely familiar, I hope. So now this is why 2, 0, 0 satisfies the BCC selection rule, whereas 1, 0, 0 doesn't. For BCC, the selection rule is that H plus K plus L should be even. That is true for 2, 0, 0. It is not true for 1, 0, 0. That's the origin of the selection rule. The selection rule is asking, when is this set of Miller indices actually a reciprocal lattice vector for this particular lattice? That's where it's coming from. You can see another case with 1, 1, 1. 1, 1, 1 makes these diagonal planes here, cutting across the unit cell here, but it would miss the BCC point. If we were thinking about BCC, we'd be missing the point in the center of the unit cell. If you went to 2, 2, 2, you have twice the density of planes here, and you would catch the lattice point in the center of the unit cell. 1, 1, 1 does not satisfy the BCC selection rule that the H plus K plus L should be even, whereas 2, 2, 2 does. Okay, so that's how you tell when you have when your Miller indices actually represent a reciprocal lattice vector. They represent a reciprocal lattice vector when they satisfy the selection rule, and they do not represent a reciprocal lattice vector when they do not satisfy the selection rule. Okay, make sense? Yeah, good. All right. One thing that's really cool about these selection rules is that, in fact, when you describe any crystal, we can describe a crystal as a lattice, any one of these 14 lattice types, times a basis. This is one of the things we went over when we did crystal structure. For example, sodium chloride, it's an FCC lattice, but then times a basis, which tells you there's a sodium at 0, 0, 0, and a chlorine at 1/2, 1/2, 1/2. The selection rules remain the same independent of the basis. Selection rules are independent in depth of basis. So there's a mnemonic for how it is that people remember this. It's frequently said that S is S for the lattice times S for the basis. So if S for the lattice vanishes, then the whole thing vanishes. Okay? So let's see if we can put some equations behind this, what I mean by S for the lattice times S for the basis. All right, so let's recall that S is going to be the sum over atoms alpha in unit cell of F sub alpha e to the I g dot r alpha. And then we can write any atom alpha in terms of a lattice point and a basis vector x. So this is lattice point, big R, lat point, and x is the basis vector, basis. So that its position, r alpha, is the position of the lattice vector r for that atom and the basis vector x for that atom. So for example, x for sodium here is 0. It's sitting right on the lattice, where x for chlorine is 1/2, 1/2, 1/2, which tells you that you take, to find the position of a chlorine, you go to a lattice point, and then you just place it by a vector x for chlorine, which is 1/2, 1/2, 1/2. So I'm just writing the coordinates of the atom in terms of its lattice coordinate and the basis displacement. Okay? All right. So then we can write S in terms of this as sum over r in lattice, sum over x in basis of F. The form factor is only going to depend on x because it only cares what type of atom you're talking about, whether it's a sodium or a chlorine. So F only depends on x here, times e to the I g, and then the position r, small r, is big R plus big X. Okay? Then we can factor this, write it as equal to sum over r in lattice times e to the I g dot r times sum over x in basis f sub x e to the I g dot x. Okay, so this is what we just calculated above. This is S for the lattice. And this here is S for the basis. So it's really pretty much strictly true that the structure factor for any crystal is the structure factor for the lattice alone times the structure factor, this factor here, for the basis. So if the structure factor for the lattice vanishes, in other words, if you're not satisfying the selection rule for the lattice type, then the whole thing is going to vanish. So it doesn't matter how complicated your basis is. If it's FCC, in order to get scattering, you have to satisfy the FCC scattering rules that H, K, and L have to be all even or all odd. Okay? Now, there's a way to interpret this statement that you have to satisfy the selection rule for the lattice alone in order to get scattering from a complicated crystal. So let's think about this picture here with sodium chloride for a second. Imagine for a second that we ignore the chlorines, just get rid of the chlorines, and then what we have left is sodiums on an FCC lattice. In order to get X-ray scattering or neutron scattering from those sodiums, you have to satisfy the selection rule. Otherwise, you get no scattering from it. Now let's get rid of the sodiums and put the chlorines in. The chlorines are also forming a complete FCC lattice, and in order to get scattering from the chlorines, you have to satisfy the selection rule. Now, if you put them both back in by superposition, it's just going to be the sum of the two scatterings, the scatterings from the sodiums and the scattering from the chlorines. So if you're not satisfying the selection rule for one of them, you're not going to get any scattering at all. So it's basically just saying that you add up the scattering from each of the pieces separately. Okay? All right. So in the next lecture, what we're going to do is we're going to actually look at some real X-ray data, and we're going to analyze the X-ray data and deduce what is in some real materials. But one of the things that we're expected to know that sort of has to be discussed is how you make X-rays in the first place. How to make X-rays. So there's two ways to make X-rays, which we may only be able to get to the simplest of them today. But the simple way, the cheap way, simple and cheap, is to use an X-ray tube. X-ray tube. This is a method discovered by Röntgen way back in around 1900, 1901. The idea is you take a great big voltage here, and you put it across a cathode on this side, just a piece of metal, on this side, and a big target on this side. And by having this huge voltage, you spit electrons off the cathode, and the electrons hit the target, and off come X-rays. So what's really happening here is that the electrons, fast electrons, kick out electrons from core orbitals. Kick out electrons from core orbitals, from core. And the X-rays you see, the X-ray lines you actually see, are mainly from other electrons falling down from the high orbitals down to the core orbitals to refill them. So see emission from transitions, from electron transitions. So an electron in a high up orbital drops down to fill one of these empty spaces in the core orbitals, and you'll see a nice X-ray line, a nice X-ray coming off. Now, the energy of that transition is basically about the Rydberg times the atomic number squared. Remember, when you have a hydrogenic atom, the energy of the eigenstates of the hydrogenic atom go as the nuclear charge squared. So, the Rydberg is 13 electron volts, but the atomic number of your atom, if you're using something like copper, something like 40. So you can have a huge, huge energy. This can be tens of kilovolts of keV, and that will correspond very nicely to what we want. Which is lambda approximately 1 angstrom. Now, there's a couple of really nice things about this technique. One thing that's really nice about this technique is, since it's an atomic transition, it's very, very sharp. In other words, it's a very sharp line, a very, very distinct transition between two distinct energy levels. Very clear energy level up here, a very clear energy level down there. And so you get a very, very well-defined lambda out of this type of technique. And this is basically what Röntgen was doing 115 years ago. Now, in the modern era, I may or may not have a picture of this. Let me see if I have it. Yeah, here. In the modern era, there's another way to make X-rays, which is sort of favored as a better technique. Incidentally, these X-ray tubes, they're incredibly cheap. You can, this is what you have in the dentist office when they X-ray your mouth, is one of these things. Or, X-ray broken bones, it's these things. And there's probably dozens of them around this building. You can build one yourself if you wanted to. But frequently, you need a much more high-tech X-ray source. And the modern high-tech X-ray source is known as a synchrotron. And it's in this picture. It's one of these big buildings. This is just down the road. This is the X-ray synchrotron source at Diamond Lab, just up the road by about 10 minutes by car. These things are about 10 to the 10th times brighter. 10 to the 10? Yeah, 10 to the 10 times brighter. More photons than X-ray tubes. than X-ray tubes. And that's actually quite useful to have for a lot of modern experiments which examine either extremely small samples or you need to collect data extremely quickly. I mean, at the end of the day, you're always counting photons. You're sort of counting how many photons are scattered in a particular direction. If you have more photons, you always get better data. Particularly if you're looking at a very small sample where it's hard to focus those electrons in on the small sample. The general idea of the synchrotron is you take this great big ring, which you can see in this picture, this synchrotron source. You spin electrons around this ring. So the electrons are going around this ring at very high velocities, up at GeVs. So giga electron volts. And then in order to get X-rays out of it, you take your electrons and you send them through a bunch of magnets. So north-south, south-north, north-south. This is known as an undulator, or a wiggler sometimes. And the idea is that the electrons going through this, they're going through very fast, and you make them accelerate through. And as you know, accelerating electrons emits radiation. In this case, they will emit directed X-ray radiation, which is extremely collimated, extremely well-defined frequency. And if you're not happy with the sort of a technique, this is sort of important to know, if you're not happy with how well-defined the frequency is, if you want to specify a frequency more precisely, specify a wavelength more precisely, what you do is you diffract off a known crystal. Diffract off a known crystal at a particular angle, and that will pick out a particular wavelength that you're interested in using. Now, whenever you're doing this, you're throwing away lots and lots and lots of the photons that you have, but if you have 10 to the 10 times the number of photons that you need to begin with, you can throw away a ton of them, and you can diffract multiple times to really specify that wavelength extremely precisely and do extremely high precision measurements. Okay, I think that's all I have to say about this. I see you tomorrow? Tomorrow.